So to find the intersection point, I'm setting these two equal to each other. X squared minus 2x equal to x plus 4. I like to keep my x squared term positive if I'm ever going to have to factor. So I'll subtract that x over to get x squared minus 3x. Subtract my 4 over. And we are in luck. This is going to factor, looking at x minus 4 times x plus 1. So these should intersect at x equals 4 and at x equals negative 1. The truth is that we could set up our integral right now without even having a picture. And this is a trick that was pointed out in class the other day. I now know my limits of integration. And if we pick a number between negative 1 and 4, we just need to know which of these two functions is on top, or which has a greater y value. If I picked a test point between negative 1 and 4, like 0, and I look at 0 squared minus 2 times 0, well, that's 0. And 0 plus 4 is 4. So that means that this function is on top because there's a greater y value there. So I can finish off my setting up our integral and have x plus 4 minus, and because I'm subtracting this term, that's going to be a minus x squared plus 2x dx. If we didn't want to use this trick, and instead we were going to actually sketch this graph, which we're asked to do in the problem, I know that this is a parabola. It's a concave up parabola because my x squared term is positive. And from looking at it, I'm going to have x intercepts at 0 and 2. This is a line with a positive slope and a y-intercept of 4. And we already know that these two have to intersect at negative 1 and at x equals 4. So I'll go ahead and use those to sketch my line in. I can now draw my arbitrary cross-section, or as the problem asks, a typical approximating rectangle. Where the base of my rectangle is dx, and the height of my rectangle is the line minus the parabola.